Okay, welcome back. In this portion of the video, I'd like to just summarize our findings here and help you understand what we can do to condense all of this information and write up our findings. You'll notice that I scanned in the document or the sheets of the lab report that I was writing on to report our data. And I do want to take a moment here to point out that, in the act of recording all of the data, we were in a hurry to do so in between each time trial. The recorded values tend to be a bit sloppy if we're not really careful while we're collecting the data. And that's typical, that's normal. You'll notice in the second sheet I included some extra information that I did not include in the first sheet and so on. So what I think is a good idea is after you've collected your data and after you've performed your initial analysis, it's definitely worthwhile to print up another copy of this sheet and really summarize your findings and report it clearly and carefully. So that's my intention here. I'm going to continue to do some facts and figuring on this sheet, but before I would turn it in, I'm going to copy it and rewrite it neatly on another sheet. And if I make this report available to you after the fact, you'll see the clean and neat copy. Now, at this point in the experiment, we're working off of a question and a hypothesis that was actually posed to us from the textbook, if you will. And we've been given this series of steps to follow. That's kind of the experiment design, if you will. And so if you're thinking about the scientific method, the process one would go through to make a formal observation, we're kind of at that point where we've collected our data and now we need to analyze it. And in the grand scheme of things, the most time-consuming part is actually done at this point. The data collection tends to be a component that takes an awfully long time. So hopefully the analysis can be done fairly quickly and reasonably, and we can interpret our results from there. So in both tables we have a total of 25 recorded times, and those 25 recorded times were separated into 5 trials. And the first thing we've got to do for each trial is to calculate the average of our 5 timing measurements. So we'll use a simple calculator to do that. And from there, within the trial, we'll calculate the average velocity. So we're working with the average time. We know the specific distance or displacement that's been traveled. So we're going to reference this formula. The average velocity is equal to the displacement divided by the average time. So that's the formula that we're going to be using for the average velocity. We also need to calculate the final velocity, or how fast the cart was moving at the bottom of the track as the plunger reached the stopping point. And that's kind of nice because in this particular case, since the object was starting at rest, its final velocity is simply 2 times the average velocity. So once we have the average velocity calculated, we'll double that, and that'll be the speed of the cart once it strikes the object at the end. And lastly, we need to compute the acceleration. This is kind of the whole goal of the project. And the formula that we're going to be using for reference here is this third example. The acceleration is the result of 2 times the distance traveled divided by the average time squared. And since we have 5 trials that we're performing these 3 calculations against, following that we'll calculate the average acceleration across all 5 trials. And the hypothesis is that this the acceleration for each of the trials should be the same, but inevitably due to human error or discrepancies in the track movement itself, these numbers are likely to be different. And so when we calculate the average, we'll then move on to calculating the uncertainty of the acceleration calculation, and that's where this delta A is going to come into play. So let's take care of the majority of the work by completing steps 10 through 12. We'll jump over to the document that we were working on just a minute ago. And again, I'm just going to use a basic calculator, and I'll probably pause the video to do this, but if I want to find the average times, all I need to do is sum these 5 times together and then divide by 5. So I'll just make a quick note. Sum these and then divide by 5. And so I'll pause the video and complete that and come back with my result in just a moment. You should do the same. Okay, and the result that I've got from my calculator off screen is 3.86 seconds. Now, we haven't had a discussion on significant figures, but since all of our time measurements were accurate to 2 decimal places, I'm going to go ahead and report my result to 2 decimal places, and that's perfectly fine for this experiment today. For the next column, we must calculate our average velocity. And again, recall from the formula in the packet, the average velocity is our displacement x divided by the average time. So in this case, we're taking the displacement of 100 centimeters and dividing by 3.86 seconds. Now, technically, we did measure this originally to one-tenth of a centimeter's precision. So we have 4 significant figures in this number, 3 significant figures in our second measurement. So the end result should be accurate to 3 significant figures. And I got 25.9. Now, to be clear, remember the measurement in the numerator is a measurement in centimeters. The measurement in the denominator, as we noted here, was seconds. And since the units combine or potentially cancel as appropriate, we need to report that as our unit of measure at the end here. And this is a good sign for us because we anticipated our velocity to be a measurement of centimeters per second. So 25.9 centimeters per second does seem reasonable. Now, according to our given information, the velocity in the final position is simply equal to 2 times the average velocity. So that's going to be easy to compute. We've got 2 times 25.9 centimeters per second. So since this is a scalar that's multiplying by a measurement value, we know that the end result is going to contain a unit in centimeters per second. And that calculated result is 51.8. We'll still retain the 3 significant figures, even though this 2 is reported as a single significant figure. But that's a scalar multiple, so it doesn't affect our significant figures. Now in this final row, we should be reminded that our acceleration in this instance is equal to 2 times the distance traveled divided by the average time squared. So if we had just one measurement, we would just divide by time squared, but since we took the average of the timing, that's why we're dividing by the average time squared. So these 3 formulas that were just given to us are going to be used in each of these columns that you'll complete on your own in just a moment. And again, with the x value being the distance over here, and I don't know if I pointed this out to you, but the description in our chart headings does a pretty nice job of clarifying where each of these components are coming from. So if you're wondering where x is coming from, well, that's this column. If you're wondering where average t or bar t is coming from, well, that's this column here. When we were working with average velocity, etc., all of that information is specified in the chart headings. And that's good practice to get into while completing these lab reports on your own. But in any event, the computation for our velocity is going to be 2 times 100 centimeters divided by the average time, which in this case was 3.86 seconds, 86 seconds squared. So if we're looking at our units, you'll notice that across the numerator, 2 times 100 centimeters is going to produce a result whose unit is centimeters. But in the denominator, we've got 3.86 seconds times another 3.86 seconds. And the units, seconds, multiply by themselves and obtain or result in a measurement of seconds squared. Now, hopefully you understand what this is trying to describe, this notion of distance traveled per seconds squared, or per second. And we can talk more about that to help you understand if you need that discussion in class. But this is a good sign for us because our result should be a measurement in centimeters per second squared. And now when we calculate the result of 2 times 100 divided by 3.86 squared, we obtain the result 13.41, or 13.4 if we retain the 3 significant digits. And we've got 13.4 centimeters per second squared as our average for our acceleration for this trial. So if I zoom out here and remind you that we've got the remaining computations to complete in each of the following rows, we also have the same series of computations that must be done in the second table as well. So I'm going to ask that you complete those computations on your own. This is part of your data analysis task. But I will pick up with some information from there. So on your own, you're going to compute the remaining elements in each row. But as far as step 12 goes, and we were asked to calculate the average acceleration, what they're asking us to do in this bottom right-hand corner is to compute the average acceleration based on the 5 acceleration values that were found here. And so I'll go ahead and share the result with you, but again, I want you to perform the intermediate tasks on your own just to make sure that you're getting the practice and understanding the process for this particular activity. And what I found after computing the average acceleration is that the end result is 13.04. I'll go ahead and include the 2 decimal points here. Centimeters per second squared. Again, as you average each of these 5 results, and they do vary a little bit, which is not intentional, but it's what happens, so that's the data that we're going to work with. But the average of those 5 numbers is 13.04 centimeters per second squared. And with this value computed, we can then move on to some summary information. Step number 13 is going to have us complete the uncertainty of our acceleration calculation. Step 14 is going to ask us to compute the percentage uncertainty. So while this is the percent uncertainty, we sometimes call this the absolute uncertainty. And with that information, along with the data points that we've measured above, we're going to create a graph on a separate sheet of notebook paper, or on graph paper, in step 15 and 16. We're going to use the slope from that graph to report our result here. And then finally, in step number 17, we'll compute this result, the percentage difference, which is going to measure the percentage difference between our calculated acceleration and the slope of our graphs. And the slope of our graphs is also going to be an interpretation of our acceleration as well, since its result is centimeters per second squared. When those steps are finished, our data analysis is over, and then we would move on to questions or steps 18 through 20 to finish out this lab, and that's your interpretation or summary. And I'll ask you to do those 3 steps on your own. So let's take a look at instructions for step number 13 here. It says to calculate your uncertainty of accelerations, delta A, and record those in the space below the data table, so in the block down at the bottom. And so we're being told that the uncertainty of a measurement is the magnitude. Magnitude, remember, is the absolute value, and that's part of the reason why we sometimes call this the absolute uncertainty. The absolute value of the largest numerical deviation from expectation. So here's some arbitrary data points that were made up as an example. The calculated average acceleration in this series of data was 22.4. So this is our expected value. This is our expectation. We think that the acceleration in this scenario is 22.4 centimeters. Not for our data, but for this sample data. This is the expected value. And as it turns out, we had quite a deviation in our trials. One of the trials measured 22.1, one of them measured 23.8, and one of them measured 20.7, etc. So these are all the different calculations that we got. And so when we're talking about our uncertainty, What I like to do is I like to find the maximum number. So let's see, I'll write this here. I'll make a note. Find the maximum number, the largest value, and the minimum value in this group. Okay? If you find the largest and the smallest value in this group, one of those will represent the largest numerical deviation, and I'll explain what I mean in just a second. So in this group, the maximum number is 24.6 and the minimum number is 20.7. Clearly, those deviate from our expected value. Now, a quick computation or a quick check tells us that our expected value of 22.4 centimeters per second squared minus our minimum calculation of 20.7 centimeters per second squared is a difference or a deviation of 1.7 centimeters per second squared. In the second case, if we're checking the maximum number, so check 1 and check 2, we've got 22.4 centimeters per second squared, our expected value, minus 24.6 centimeters per second squared, and that ended up being a negative 2.2 centimeters per second squared of deviation. So we're uncertain about our measurement, and in this particular case, the largest amount of uncertainty is 2.2 centimeters per second away from center. Now, we tend to take the absolute value of these to measure the magnitude of the difference, right? The distance between the expected value and the actual value. And so clearly in this case, the absolute value of negative 2.2 is greater than the absolute value of 1.7. So that's why we're going to say that 2.2 centimeters squared is the deviation or uncertainty for this data set. With our data set, you have a, where did it go here? You've got a completed copy or set of data. And according to my calculations, the maximum acceleration was 13.73 and the minimum acceleration was 11.94. So therefore, when I calculate the uncertainty of the acceleration, sorry, not the average acceleration, but the uncertainty of the acceleration values, one calculates to be 13.73 minus 13.04 centimeters per second squared, and the other calculates to be the absolute value of 11.94 minus 13.04 centimeters per second squared. Now, since we're using absolute value bars, the order of the subtraction doesn't matter. The end result always becomes positive. So it's okay if you write those out of order as long as you are using absolute value bars. And I say that because I know some of you realized that I wrote this in the opposite order of the instructions, but that's okay. Mathematically speaking, we'll get the same result. So in this case, it looks like our uncertainty is 0.69 centimeters per second squared, and in this case, our uncertainty is 1.09 centimeters per second squared. So when we report our uncertainty, we want to select the larger of the two. And so in this case, we'll report that 1.09 centimeters per second squared is our uncertainty. And at this point, I would ask you to refer to step number 14 to determine the percentage uncertainty. The formula is provided there. As I compute the result, we see 8.37% as our percentage of uncertainty. Part of your write-up should include the work shown to complete the percent uncertainty. Now, completing this information on one table is a good start, but don't forget we must do the same for the second table as well, and the process is done much the same way. In fact, it's done in the exact same way. And to give you something to check against, I'll go ahead and provide some end results in this particular instance. And for the average acceleration in this group, I computed 27.0 centimeters per second squared. The uncertainty is 1.82 centimeters per second squared, and the percentage uncertainty is 6.73%. And please make sure that you show your work for these calculations, either in your lab packet or on a separate sheet of paper, so that I can see how you obtained your results. If for some reason yours differ from mine, that would be okay, as long as you can show support for your calculations. Now, ideally, we'll all get the same answers because we are using the same data. But if I keyed in the wrong number or calculated something incorrectly, which has been known to happen, then my numbers in this video will differ from yours, and it's entirely possible that you've got the correct result, and your work will show that. So let's see if we can finish this out now. We're going to jump back to step number 15 and double check the instructions there. Step number 15 asks us to construct a graph for each table, plotting the final velocity, VF, on the vertical axis and the average time, T bar, on the horizontal axis, and be sure to include the origin 0, 0 as a data point. We will fit a straight line. Now, we're using quotation marks here, fit, so we're not actually going to do a true mathematical analysis. This is just a manual guess. Manual guess, not a true data regression analysis. So that's okay. We'll save some time there. And then we'll determine the slope of the line in each of these graphs and then report that slope in the data table. So what we're trying to stress here, or trying to create at this point, are a series of data points whose x values are the average time value, and the y value is the final velocity. So we're using these two numbers to create a data point and graph. So we've got, in this case, 3.86 seconds as our x value, and then 51.8 centimeters per second as our y value for that coordinate. And you'll have the same for this row, this one, and this one. So we're going to have 5 data points from each of these measurements here. And you've got your own completed table to look off of, so that's where the data is going to come from. And we also have an additional data point which should be used, and that's going to be 0, 0, which should make sense. If the cart was traveling for 0 seconds, then it's built up a final velocity of 0 centimeters per second. So even though that wasn't a recorded data point, that's definitely one that can be used in our graphs. Now, I have provided blank graph paper for you to use if you'd like to print some out. Feel free to download that and make copies of it for future reference, or if you want to use your own plain graph paper, that would be okay too. And so after labeling your graphs page, what we need to do is we need to create an XY axis. And I'm going to cheat just a little bit since I have technology on my side. I would recommend that you take the time to carefully draw vertical lines and horizontal lines that are perfectly straight and neat. I'll label this. In this case, we'll just call it graph 1 because it's associated with table number 1. And actually, since I have a full sheet to work with, I'm actually going to move this down and give myself a little bit more space to work. This way I can label the graph a little bit more carefully, and if I needed to extend the lines or adjust the scaling, I can do that too. Now, when I consult the data for table number 1, it looks like our final velocities are around 3.5 to 4 seconds. And since we have to include the data point 0, that's going to make our data appear to be clumped together towards the end. But as far as my scale goes, I think every 4 grid lines in this particular sketch would be appropriate. And it's worth noting the axis is our velocity final, and this is measured in centimeters per second. It's good to have axis labels. Now, as far as our vertical axis goes, oops, and I totally messed that up. The vertical axis should be our final velocity. The horizontal axis was time, the amount of time that it took for the cart to travel. So my mistake there. The horizontal axis does extend from 0 to 4, but this is a measurement of average time, the average time trials, and those were measured in just seconds. It's our vertical axis that represents our final velocities, and those are measured in centimeters per second. And the final velocities here range in the 40 to 50 centimeters per second. So on this particular graph, the scale of every 3 grid lines representing 10 centimeters per second would be appropriate. If you'd like more data, more clarification or precision with your graphs, of course you can adjust your scale. Keep in mind that I want 2 graphs on this page, not just 1. But as far as my computer screen goes, I think this is a good fit. If we plot the data points from the table, we actually see a cluster of data points that look like this. And again, this is where adjusting our scale might make a little bit of a difference when we generate our result. But having this data point down below in the bottom left-hand corner and this cluster of data points in the top right-hand corner, I think is okay, because if we were to plot this trend line, a line that seems to be going through all of these data points, we see a result somewhere around here. In fact, if I use a program like Microsoft Excel to generate the graph for us, we see a very similar shape as well. And you can see how the scaling is a little bit different here. So one of the last things that we're being asked to do is determine the slope of this line that fits. And fortunately for us, this particular line seems to strike some lattice points or intersections of these graphed points pretty nicely. And again, the benefit of having a linear equation is that the slope is consistent everywhere. So as long as I can find 2 points that intersect at a nice lattice point, I'm going to use this one. Actually, I probably won't use that one. I'm going to use this one instead. And let's see, maybe this one. As long as we can find 2 data points that fit nicely on the intersection of 2 grid lines, then we're going to be in good shape to calculate our slope. I chose these because they're easy to identify. On my x-axis, I have 0.75, and on the y-axis for this position, I have 10. If I had selected this point here, I've got an x value of 1, but a y value of 13.3 repeating, and so that's why I avoided that data point. This data point is going to be 1.5 on the x-axis and 20 on the y-axis. So when it comes to slope, we know that we're going to subtract the 2 y values, so 20 minus 10 divided by the difference of the x values, 1.5 minus 0.75. And we can't forget that our numerator's units are centimeters per second, and our denominator's units are seconds. So when we calculate the end result, we're going to have a measurement, or a unit, whose measurement is in centimeters per second squared. Centimeters divided by second divided by second. And using my calculator off screen, this computes out to 13.3 repeating centimeters per second squared. When we jump back to our lab report, we can now report that number as our slope in Table 1. We've got a slope of 13.3 centimeters per second squared. And then finally, we can compute our percentage difference. Now on the handout, I'll go ahead and give this one to you here so that we can finish out the video. On the handout, we were told that our percentage difference is equal to the slope minus the average acceleration, absolute value. Again, order doesn't matter here as long as we contain the absolute value bars, divided by average velocity times 100% to report it as a percentage. And so with the slope of our line being 13.3 and our average acceleration being 13.04, those two were awfully close, which was nice to see. The percentage difference ended up calculating out to be 1.99%. of a difference. And so now we have enough information to go ahead and finish the final questions in our report. Question 18 asks you to compare the percentage difference, which is it's sort of a percentage uncertainty now that we've included the 0, 0 point on the graph. But we're comparing this percentage difference to the percentage uncertainty from before. And you should discuss why these are different and which one is, quote, better. Question 19 asks us to discuss at least one systematic and one technique error. So read your textbook to really understand the difference between systematic and technique errors. Or I suppose you can look up descriptions online too. And once you've identified any of those errors in this particular lab, you can describe how that may have affected our results. And then in number 20, try to connect what we've done today to something that you've experienced in the real world. And if you're having trouble with number 20, just remember that the title of this lab is Accelerated Motion Downhill. So if you're having trouble thinking about where in real life you might see some of these concepts, just think about, well, what are some objects that accelerate as they roll or move downhill? So that about does it. That concludes the portion of the lab that I wanted to share with you. You've got a fair amount of time to spend working on your write-up and calculations. Please make sure that your final copy of your write-up is prepared and ready to be turned in 1 week from today, so next Friday before the start of our following lab. Thanks for watching.